Hello, students. Hope you're doing well. I wanted to go over section notes. This is my 1.1, as you can see on my screen. It's the first section in the book, and uh, students wanted me to explain it, some things from this, so I thought maybe I'll go over it, whole of it, and if the recording gets bigger, I'll just split it into two parts. So before starting, um, before delving into core linear algebra, which is about vector spaces and converting them to matrices and all that, we start with system of linear equations and we see how we can use matrices to solve the system of linear equations. Now, in your earlier courses or earlier math, whatever it was, pre-cal, college algebra, or calculus, you might have seen system of equations in two variables or maybe three variables. uh, Usually they had like two equations in two variables or three equations in three variables. That's by far you have seen mostly. And what were the scenarios when you had two equations in two variables? As you can see on my screen, that the lines are intersecting. Of course, when there is an equation in two dimensions and there are two variables associated like x and y, then it represents a line. Now, if you have two equations, then how can these lines be represented in the two-dimensional plane, in two dimensions? So they either they could be intersecting, or they could be parallel, or they could be overlapping. So those are the three options uh, we will be taking into consideration for higher dimensions as well, because certain things can happen in these things can happen in the higher dimensions as well. So, for example, for the first one, you can see unique solution, the lines are intersecting, then they have parallel lines, they never intersect, or we have overlapping lines. And there are examples written on this screen, on this document as well. Now let's move on to the higher dimensions, which are three dimensions. Now in three dimensions, we have again we have planes now instead of lines. Then how can there be infinitely many solutions? How can there be one solution, or how can there be no solutions? So the three pictures, let's look at this one. The three pictures are one example of let's say this one is infinitely many solution. The first one is infinitely many. Then you have one solution, and that's the only example of one solution. I mean, that's how planes can intersect. All three planes are intersecting at a point. Um, and then you can think about three walls in your house, that if you're sitting in your room and you can see three walls, the roof and the wall in front of you and on the side of you, they three are intersecting at a point. So that's one solution. No solution means three planes are parallel, and then infinitely many solutions, as you can see, they intersect in a line, right? So two of them are intersecting and the third one is crossing in between like a line. So these are some of the examples of what can happen in three dimensions. Now we will be, if you think about techniques that we have used in two dimensions, those were substitution and elimination. Um, those kind of they get tedious once we move to higher dimensions. So we cannot apply I mean, we can apply, but it's not easy to apply substitution and elimination in your higher dimensions. So what matrices do, matrices make our life easy when we move from a when we move when we do a system of linear equations, when we try to solve system of linear equations in higher dimensions. So first of all, to start off, what is an augmented matrix? Given a system of equations, let's say this is my system, an augmented matrix is the matrix of the coefficients of x1, x2, x3, or x, y, z. Let's say we are in 3 by 3, and those are written column wise, and the last column has a column of constants. So if we are in a 3 by 3 system, your augmented matrix will have three rows corresponding to all three equations and four columns. The first three columns will have the coefficients of x1, x2, x3, and the last column will have the coefficients of the not the coefficients, the constants. So for example, x1, 1, then -2 for x2, and then 1 for x3, and then 0, and so on. And we usually we break this to see that the last column has constants. We use this dotted line in between so that the first three columns represent equations and the last one is a constant. Then we can apply certain row operations to the matrices and it does not change the solution of the system. So the row operations are you can interchange two rows, it doesn't change. I mean, if I interchange two equations in there, the solution doesn't change. Similarly, if I add or subtract two rows, it doesn't change. If I add or subtract two equations, it still passes through the same solution. Okay, for example, I don't know how much you know about vectors. You might have seen them in trigonometry. If you have two vectors, the resultant vector also passes, the addition or the subtraction vector also passes through the same point as the given two vectors. Um, then you have scaling. If I multiply an equation by a scalar, I mean, it doesn't change the equation, right? So those are kind of obvious things we can do with the matrices, changing or scaling or adding or subtracting two rows. Now, these are the two forms, echelon form and reduced echelon form, which we want our matrices to look like. Okay, now these are the simplified versions of the given augmented matrix. Using those row operations, those were discussed here, those three row operations, I'm going to convert my matrices, my augmented matrices, into one of these forms. And after I convert it into one of these forms, I can easily tell what the solution is. Now, what is the difference between the two forms? Let's read. In the echelon form, all non-zero rows are above any rows of zeros. So once you're converting an augmented matrix into echelon form, the row of zeros must be at the end. Okay, each leading entry of a row in a column is to the right of the leading entry of the row above it. So what that means is leading entry means, for example, if I'm converting, let's say this is my I'm gonna convert, let's see, I'm gonna convert this one here. I cannot edit it, but let's say this is my first entry one. So the next leading entry must be diagonally each leading entry of a row in a column to the right of the leading entry of the row above it. So these should be diagonally arranged as the leading entries in the row. Now, all entries in the column below a leading entry are zero. So, for example, this is my leading entry in a row. Then below these, everything should be zero. Then I come to the second leading entry, which is here. Below this, everything is zero. I'm not talking about above what's happening, but below that leading entry in a row, everything should be zero. So that's my echelon form, first of all. For example, this is the matrix given. First of all, I would like to convert this 5 right here to 0. So that's what I did. I did R3 minus 5 R1. R3 changes to R3 minus 5 R1. So you multiply 5 by R1 and subtract it from R3. So now you're doing scaling and then you're subtracting one row from the other. So that's how your row 3 changes, 0 plus 10 and then minus 5 minus 5 minus 10 and then 10 minus 0 is 10. Then you want to convert this 10 to 0. I can divide everything by a 10 in row 3. That will be 1, negative 1, 1. I can do that. If you don't want to do that, just make this entry as 0 right here. So that becomes R3 minus 5 R2. And now I'll be using this row, second row. I won't be using my first row. I cannot because this entry is 0. So second row I'll be using and then similarly I'll be converting this as 0. So that's my echelon form, right? There is no row of zeros. If there was, that should be at the end. The leading entries should be arranged diagonally and everything below the leading entries in the rows should be 0. And I'm done. So from here, since my columns are x1, x2, x3, first of all, my 30x3 is negative 30, which means x3 is negative 1, and that's from my row 3. Then from my row 2, 2x2. So look at these numbers right here. 2x2 minus 8x3 equals 8. Plug in the value of x3. you get x2 as 0. And similarly, from row 1, you have x1 minus 2x2 plus x3 equals 0. Plug in x2 and x3, you get x1 equals 1. So we have a solution, actually a unique solution in this case. All three planes intersect at 1, 0, negative 1 in xyz um, in your x in 3D system, right? In 3D coordinate system. Now, if I want to convert this matrix into reduced echelon form, there are two more conditions. The first condition, the leading entry in the rows must be 1. And also, since we converted everything below 0, now we have to convert everything above that leading entry as 0 as well. So if I continue to convert this given matrix into your RREF form, I would be making this 2 as 1 and this 30 as 1 first, and then do my backward phase, not backward substitution, but backward phase of row reduction to these three entries right here. These three entries right here, converting these three entries as 0, negative 2, 1, and negative 8. And that's what I have done here. So first I converted R2 by 2, and R3 by 30. So I have my leading as 1 now, which is one of the requirements of the reduced echelon. And now I'm going to convert first negative 4 and 1 as 0 using this 1. So that's what I have done, R1 minus R3 and R2 plus 4R3, and converted these two entries as 0. And then I have converted this entry, the last entry, as 0 because I have this 1 as the leading in row 2. So I have R1 plus 2R2. Now in this case, the interesting thing is in this case, you don't have to do any backward substitution. The last column is actually your solution. 1, 0, negative 1 is actually your solution. And that's the benefit of your reduced echelon form as compared to your echelon form. Now in echelon form, we did certain calculations here, and that's called backward substitution. Whereas in the reduced echelon form, the last column is actually your solution. Couple of things to note: a matrix has unique reduced echelon form. In calculators, computer programs, you please look at my calculator usage video. It's posted in the content. The calculator, it's denoted by RREF, row reduced echelon form. Um, and then you can read these after we calculated. This is what I have discussed: backward substitution or reduced echelon form. You can do any of these things. Okay, this is a note about your efficiency. It's better to calculate. That's what it is saying. It's better to calculate reduced echelon form in applications. Okay, so there are some benefits of that, and I would love to hear if someone, if you know some benefits, if you are in the industry. Unfortunately, I don't have exposure to these things because I'm in a teaching field. But if you are in an industry where you are using these and can share some of the insight on how one form is has more advantages over the other one, then I would be happy to listen to that. Okay. Now, as discussed before, not every solution is a unique solution. These are the two examples here, again, two pictures here where you can see no solution. But once you have a system of equations, how would you know from a matrix, from an augmented matrix, that it has no solution? So let me make it a little big here. As you can see, this example, this is from the book, and they have done certain row operations on this, and the row last row has come out to be 0 0 0, which is the coefficients, and the column entry is still non-zero. Sorry, the constant entry is non-zero. Now this is in the case of augmented matrix. If an augmented matrix, the last row, once you're reducing your augmented matrix, the last row looks like this, it means there is no solution because 0 cannot equal to 15. Okay, 0 plus 0 plus 0 cannot equal to 15. So in those cases, and there are, you can read about the operations which are done here, you will be getting no solution. Now, in the case of infinitely many solutions, suppose this is a matrix, augmented matrix given, which is 1, 2, 3, 4, 5. So 3 by 5 system, 3 equations and 5 variables. And of course, the last one is the column of constants. And converting this matrix into reduced form, I have used my RREF from the calculator, and that's what we get. These That's how the matrix looks like, and that's your reduced echelon form right here, because you can see the leading entries are 1, and wherever those leading entries are, all the other entries are 0, right? So now there is another concept which we can take into account here, which is pivot columns and pivot positions. A pivot position in a matrix is a location in A that corresponds to the leading one. So this is my pivot position, this is my pivot position, and this is my pivot position. So in C1 and in C2 and in C5, row 3, column 5 is a pivot position. Wherever those pivot positions are, those columns are my pivot columns. Okay, so C1, C2, C5 are your pivot columns here. Now, what that means is that corresponding to C1, C2, C5, I have let's look at the example first. So if I do my backward substitution here and I'm getting 3 pivot positions, it means 2 of my variables will be free variables in this case, and 3 will be my basic variables, which will depend on the free variables. Now, from the last pivot position, I can say that x5 is 4. Now, from the second row, I can say x2 minus 2x3 plus 2x4 is negative 7. And the two columns which are non-pivot will correspond to my free variables. So x3 and x4 will be my free variables. Last column, last row tells me x5 is 4. The previous two rows give me these two equations. Clearly, x3 and x4 are my free variables. Solving x2 and x1 in terms of x3 and x4, I get this 7 plus 2x3 minus 2x4 and minus 24 plus 2x3 minus 3x4. So the solution set is, I'll go with this notation because that's how you will be doing in MyLab. x1, whatever it came out here, negative 24 plus 2x3, similarly x2, then x3, 4 free, x4 free. Free means it can take any real value, and x5 is just single point 4. This kind of solution written is called solution in parametric form. And the x1, x2, x5 corresponding to the pivot positions are called basic variables, and x4 and x3 and x4 are free variables. So these are some of the questions I think you were answering in your discussions. A system is called consistent if there is at least one solution, and infinite or unique both are consistent. If there is no solution, then it's inconsistent. Another way to look at an inconsistent system is when augmented matrix has last column as pivot column. So that's another one, another way to look at inconsistent system. So that's it for me, and let me know if you need more explanation on any of the things or any of the other sections. That's it. Thank you. Bye.